is depicted by a unique symbol. And there are different methods. You find them here. So I will introduce these 6 methods to you according to the book of Slocum and colleagues. And the first one is equal intervals method. And all the methods use the same data here. So it's about the foreign-born residents for counties in Florida, in the United States, in 1990. And we always classify this data into 5 classes. Equal intervals method of classification is one of the, maybe it's the simplest method available. It's just that each class occupies an equal interval along the number line. So it's here are the basic steps. It's simple to compute these numbers. And we stopped the last time after the map. This is the number line down there, and you have the 5 classes here, and the counties, all those counties, these areas you see here in Florida, they are here represented along the number line as these dots. So here you have the values. There is this outlier here with nearly 45, and most of the counties, the data of most of the counties lies down there between 0 and about 15. With this method, this is one of the disadvantages. You create also classes here without members. So class 3 and 4, these 2 shades of gray you cannot find in the map because there is no number, no county here for these numbers. Now, what are the advantages of this method? The 5 steps are easy to calculate. The resulting equal intervals are easy to interpret for map users. Easy to read legend with no missing values or gaps. So in between the classes, there are no gaps. So it's always where one class ends, the next class starts. This is meant here. You will see then with other methods that this is not always the case. The disadvantages are class limits. This is the main disadvantage. Class limits fail to consider how data are distributed along the number line. So these 2 classes I just mentioned, that classes 3 and 4, they are kind of wasted because there is no observation, no county in these 2 classes. Then the second method is the quantiles method of classification. Data are ranked, ordered, and equal numbers of observations are placed in each class. So it's about equal number of observations. Different names for these methods are used depending on the number of classes. So 4-class quantiles are referred to as quartiles. And 5-class quantiles are referred to as quintiles. So that's what we have here because we need 5 classes. So our quantiles are quintiles. The first step, compute the number of observations in a class by dividing the total number of observations by the number of classes. Then you know 13.4. is the number you have to deal with. The second step, determine which observations should be placed in each class by progressing through the rank-ordered data until the desired number of members in a class is obtained. Try to place approximately the same number of observations in each class. As the result from step 1 is 13.4, the numbers fitting best are 13 or 14. But caution, identical data values must not be placed in different classes. If necessary, place different numbers of observations in some classes. So of course, this is not possible. It would be a manipulation of the final result. So it doesn't matter if in one class there are a bit more than in another one, but it should be about the same. The next step then, step 3, define the limits for each class shown in the legend. In general, there are 2 ways to do this. And these 2 ways apply also for other classification methods. The first is specifying the lowest and highest values of members in a class. For example, the 14 members of class 2 range from 1.5 to 2.7. And so these limits would be shown in the legend. Or B, computing a class boundary as an average of the highest value in a class and the lowest value of the next class. For example, the upper limit for class 2 would be 2.7 plus 3.1 diverged by 2, then it would be 2.9. Of course, this has to do with the situation in the legend then, if you have these gaps or you don't have these gaps. And this is then a situation with quantiles. So we have these 5 classes. These are the boundaries here. So you see 1.4 and 1.5. So here is not really a gap, as there is no number in between from our data. But from 2.7 to 3.1, there is a gap. So this is meant with the gaps in the legend. And it's possible to find or to use the number in between. Here it would be 2.9. Then we would have here 2.9 and 2, including 2.9 here and here above 2.9, for example. Then there is no gap in the legend. These are these 2 methods I have just talked about. And you see now here, the size of the 5 classes is, of course, very, very different. So this is obviously a big difference to the first method. Here, class 5 is very big because we need the same number of counties in each class. And there, near the lower values here, there are many, many counties. You see many dots here. So the classes are very small, the class limits. So here it's just about 0.8. So this is 0.8. But here it's 6 from 6.8 to 45.1. So you see this big difference. And of course, the map looks totally different if you compare method A and B. Now, what are the advantages of this method? The 3 steps are easy to calculate. So this is like with the equal interval method. The percentage of observations in each class will approximately be the same because an approximately equal number of observations fall in each class. So that's just obvious. And this facilitates interpretation. So if this basic idea is clear to the users, it's easy for them to understand what's going on here. Quantiles are useful for ordinal level data because class assignment is based on rank order. That's an important point because this is an outstanding feature, let's say, of this method. So if you have ordinal level data, and ordinal level data is ranked, so you have a first, a second, a third, a fourth, and so on. If you have such data, then quantiles is your choice for classification. If enumeration units are approximately the same size, so enumeration units are, for example, administrative units, like here, these counties within Florida. These are enumeration units. So if they are approximately the same size, each class will have approximately the same map area. So this is, for example, useful when comparing maps. Therefore, you can only compare this order level data from different maps, for example, different times of the same area. Then it's possible, even if the sizes are not the same, but it's still better if they are the same. But you can also compare, for example, different states of the United States. You can compare, let's say, Florida with Louisiana, and this makes more sense if the enumeration units, here the counties, are about the same size. Of course, they will never be the same size exactly, or you have some artificial units. That's also possible. If you have a grid system, for example, with all areas covered by squares of the same size, this is a different story. We are not working with that here. And the disadvantages: class limits fail to consider how data are distributed along the number line. As you see, these big differences, of course. And especially in the fifth class, this outlier, this very high number, about 45, is included now in the same class as several values with lower magnitude, about 15 or even lower. So they're in the same class. They're treated as the same. They get the same color, the same gray value in the map. So they look like they are the same for the user. But of course, this is irritating and makes it more difficult to interpret the numbers, the data that is behind the map correctly. And depending on how the limits for each class shown in the legend are defined, there might be gaps. For example, the highest value in class 2 is 2.7, and the lowest value in class 3 is 3.1. This results in a gap of 0.4. So I've just talked about that. The gaps are problematic because readers might wonder why they occur. So readers sometimes think, what's going on here? Are some numbers missing, or why is there a gap? However, they do permit the legend to reflect the range of data actually occurring in each class. So it is not a disadvantage. It's more a problem that some readers are not familiar with these gaps. So it might be useful to give some information why there are gaps, because we get a more precise impression of the data if we have these gaps. The third method is the mean standard deviation method of classification. Classes here are formed by repeatedly adding or subtracting the standard deviation to or from the mean of the data. Step 1, calculate mean and standard deviation from the raw data. For the Florida foreign-born data, the following formulas were used. And again, I've mentioned that the last time, you don't need to learn any formulas. So I will not ask about formulas, but you have to know what's going on. So you need to understand how this method works. It would be, for example, you have to know about the steps, what the steps you have to do to apply this classification method. But you don't need any details about formulas. You don't have to write down formulas, and you don't have to compute numbers with the formulas. So it's necessary to know about these details. Of course, these are simple formulas, and you already know them from middle school. But yes, for those who are not so familiar with formulas, no problem. You just have to understand what's going on here. And it should be noted that there are also different formulas for samples and populations. So a sample is just, you have just a few numbers, and they represent a population. That's a sample. And the other thing is a population. That means you have all the numbers. So when it's about Florida, you have a population here because it's about all counties in Florida, so it covers the whole state. And here, formulas appropriate for samples were used because of the relatively large number of observations. Similar results would be obtained with population formulas, but this is just background information. Then the second step, add and subtract once and twice the calculated standard deviation to and from the calculated arithmetic mean to get the calculated class limits. Third step, adjust calculated class limits to create legend limits in a way that identical values cannot fall in two different classes. So again, if you have identical values, and we have this for some of the counties, we have the same number of foreign-borns. So, and these counties, of course, they have to get the same gray shading. They have to lie in the same class at the end. And the limits of the lowest and highest classes reflect the lowest and highest values in the data. So for our data here, for the Florida foreign-born, the following results were obtained. So we have the normal distribution limits, the calculated limits, and then the legend limits. So this is important then, for the legend, but also, of course, to clearly define where lies each of the counties. And this then is the result. And yes, you see now here we have, in fact, only 3 classes. So you cannot find the first 2 in the legend. Why? Because we have negative numbers here. So this has to do with the computation. It doesn't make sense in this example, in fact, because we have no negative numbers, and there cannot be negative numbers. So there cannot be a negative number of foreign-born citizens. So it's 0, or there's a certain number of foreign-born, but it's not below 0. And you see, this is, of course, one of the problems also for this method. And for the rest, you see then in the largest class here, there is just this one outlier, which makes sense because it's so different from the others. And you see immediately in the map, okay, here is this county with most foreign-born. Then you have 3 counties, 3 dots, these 3 counties here in the class 4, and all the others are in class 3. Now, what are the advantages? This method considers how data are distributed along the number line. We have seen that in the 3 classes. If the data are normally distributed or near to normal, the mean serves as a useful dividing point. So you know the mean divides the numbers or the data into 2 halves. So 50-50. 50% of the data is below and 50 is above it. Therefore, it is a useful dividing point, but only if the data are normally distributed, especially if an even number of classes is used. For example, 6-class map. The legend contains no gaps that might confuse the reader because it's computed. The disadvantages: understanding of some basic statistical concepts is required because users need to know what mean and standard deviation stand for. Otherwise, they have this legend and they have no idea why it's computed in that way. Why are these class borders used and so on? So it's important that the concept behind is clear for the users. And further disadvantages: it does not work well with data that are not normally distributed, as in our case here, as in the foreign-born data example, in which the 2 lowest classes contain solely negative values and therefore have no members. If you check the dispersion graph below the mean standard deviation map, you will see that the data distribution is positively skewed and not normal. So I will show you that on the next slide. So this is the normal distribution. I'm also sure you know about that. It's just a repetition. Maybe you're not so familiar with the English terms. So this is called the standard normal distribution. Also, other names are the normal curve. So it's a short name, or simply the bell curve, because it's a bit shaped like a bell, like a cross section of a bell. And you have these Greek letters here. Here, this Greek letter in the center. This is nu. It's pronounced nu. This one denotes the population mean. This is the mean. So you have 2 halves of the data then. Sometimes you might also see this one here. It's pronounced x bar. X bar. This denotes the arithmetic or sample mean. So mean is mainly used for the population mean. Just talked about this difference. There is another small Greek letter. This is, you see here, 1, 2, and 3. These are sigmas. So this is pronounced sigma. 1 sigma, 2 sigmas, 3 sigma. This one denotes the standard deviation. Sometimes you find also just S instead. So this is 1 standard deviation, this is the 2nd, this is the 3rd, and so on. And these are then the class limits. You just have to compute them with your data to get the exact numbers. And about the skewness. It's this graphic here has a poor resolution, but it's possible to read everything. Here you have this difference between negatively skewed. So if the mode is on the right-hand side of the median, the mode is where you have most of the data values. And of course, in the bell-shaped curve, mode, mean, and the median are just in the center. So the median divides 50-50. The mean is the middle value, the average value, And the mode is the value that is most often, the single value most often within the data. So here the value that appears most often in a set of data values. Here you have the definition, and the median, the value separating the higher half from the lower half in a set of data values. And you see that the position of these three statistical numbers are reversed if it's positively skewed. So skewness is about this asymmetry in the curve. So this is the bell-shaped curve. This is a normal curve. And this is when data is skewed. And I go back. Here, it's clearly positively skewed when you look at the numbers. So here are most of the numbers, and here there are only few numbers. So it's what we see on the right-hand side. Here, this shape is that describes, or this curve describes our data distribution in our example. And this method again works best and should be used only if you have a normal distribution, a bell-shaped distribution. Here's another example where you see it works better. Also, as you see, it's not a perfect symmetry. Also not here. This application of the mean standard deviation method of classification is about median house values in the Seattle, Tacoma, Bremerton metropolitan area. So this is in the state of Washington. So it's here you have then Canada, Vancouver area up there, and here is US. So we're in the northwest of the United States, Seattle, and you have here this legend about the median house values. The mean is computed, and here they don't write down the numbers. So the actual values, the median house values, are not here. They just write down the first, the second standard deviation, the third standard deviation. This still gives you an impression of the situation in the map, of course. But it would be more interesting with actual numbers for the median house values instead of just indicating the number of standard deviations. But this is also to show as an example how these different standard deviations are applied here, how the method is applied, this classification here. Then the next one, the maximum breaks method of classification. Individual data values are considered, and those that are more similar are grouped. So this is the basic idea here. Step 1, order the raw data from low to high. Step 2, compute the differences between adjacent values. Adjacent values are neighboring values. So you have a line, you write down all the numbers from low to high, and then you check out the differences between each of the numbers, but only the neighboring ones first. Step 3 then, order the differences from high to low and select the largest of them to serve as class breaks. The 4 largest for a 5-class map in our case. So we need 5 classes, therefore we would use the 4 largest class breaks. Step 4 then, define the limits for each class shown in the legend. In general, there are two ways to do this, and this is the same as before. Specifying the lowest and highest values of members in a class, or computing a class boundary as an average of the highest value in a class and the lowest value of the next class. So this is just the same as in quantiles, step 3. And this is what you get then. So here on the number line, you see immediately these gaps. There's a huge gap here, because in this class here is only a single number, and also in the third class here. So just one county lies in this class. This is for the highest number, we know that already. And this one here is for the third class. So it's also only one county with this gray tone here. This is 12.2. And we have then just two counties in class 2 and 4. So in class 4, these two, and in class 2, these two. And from here, all the counties have the same gray value. They all are in class 1. You see that here. So this is class 1. And of course, now these class limits define very well the range for the range within each class. And you see that here along the number line, there were no counties. So these are the breaks, the maximum breaks. That's where the name comes from. So if you check out the differences between counties of the same value, so these, of course, they have the same value. Here they're very tight. So nearly each possible number, if you talk about one decimal position, then we have for each decimal position, we have counties here, one here or several like here. Here is a small break, but this break is larger. So the 4 largest breaks are these open spaces here along the number line. And these 4 largest breaks are used to divide all the counties into the 5 classes. That's why I like this approach in the book of Slocum and colleagues, because this is really very well done. We have always the same data. We have a map and a number line we can compare. And so I think it's relatively easy to understand the basic ideas behind these different classification methods. So what are the advantages now of this maximum breaks method? The steps are easy to calculate, and it considers how data are distributed along the number line. So that we have these gaps is in fact the basic idea of the method. I just talked about that. So the classes reflect very well the distribution. Disadvantages: by paying attention only to the largest breaks, natural clusters of data along the number line might be missed. So for example, peaks and dips within class 1 are ignored. Peaks and dips, what is meant? I go back. These are the peaks, and this is a dip here. So within this class, we have certain clusters and differences. And within this class, we have no difference, of course, here. They are all classified in one class. So for the user, and the user usually does not see the number line. So the users usually only see the map and the legend, and then they don't know. They don't know in this quite large area where are the differences. Of course, they are smaller. Therefore, it's acceptable, I think. But sometimes you want to know, are there some regions here clustered with the lowest numbers? Here, for example. What about those with a bit higher number? So this is meant here with the peaks and dips within class 1. And depending on how the limits for each class shown in the legend are defined, there might be gaps. So, of course, I go back again. You could compute it in a different way. So you can close these gaps. You can close the gaps here, but again, as it is the maximum breaks method, it's somehow natural to have these gaps. But still, it might be difficult for users to understand that. So users look at this legend and they don't understand why is here 8.3 and here 10.1. Is there nothing in between? Yes, that's the reason. There is nothing in between. But for some, this is strange. And also that here is just one value. Why is there no lower and higher class limit here? So in fact, this gives you more precise information, but for some it might be confusing. The next method then is the natural breaks method of classification. So we just talked about the maximum breaks, and now we talk about the natural breaks. Graphs, for example, the dispersion graph or histogram, are examined visually to determine logical breaks. So what we have along the number line with all the counties, the dots there, you could say this is also a dispersion graph or histogram. We can just visually look at this distribution of the different numbers to check out if there are some logical breaks or clusters. So we just talked about that for the first class. There are some differences within the first class. There are these, there are some numbers or lower numbers where there are more counties than in the higher numbers, for example. So that means to minimize differences between data values in the same class and to maximize differences between classes. So maximum breaks, the method that we just talked about before, is about maximize differences between classes. But here it's also about minimizing differences between data values in the same class. So within a class, differences should be minimized. Step 1, examine the dispersion graph or histogram carefully. Step 2, decide where the natural breaks are that best separate the most obvious clusters in the data values. Step 3, define the limits for each class shown in the legend. In general, there are two ways to do this. Again, you can specify the lowest and highest values of the members within this class, or you can compute boundaries. The first often results in gaps, and the second, you have computed a number that exactly defines the boundary between the classes, so there are no gaps with B. And this is then the result. So it looks a bit different to the maximum breaks method. As you see here now, we have 2 or even 3 in part. The third class is also involved here. For these large amount of counties, so most numbers are here, therefore it makes sense to have more classes here. And then we have class 4 here, and again, just one class for the outlier for the highest value, because it's so different from the others that it totally makes sense to have this class with just one value here, 45. So we have the gaps here between the classes, but as you see here now, we have a better distribution of the gray values in the map. So we see more differences here in the lower numbers. Although these differences are small, but this we can see also from the legend. Here we have, of course, a smaller range than, for example, here. So the map looks more different than maybe the numbers in the first moment would suggest, but we have this additional information of this number line here, and therefore we know why we have this distribution and this result with this classification. The advantages are of the natural breaks method. The steps are easy to calculate. There's even no calculation necessary. So this is just done visually without calculation, or nearly without. So if you like to compute the class levels at the end, then you need some smaller calculations. It considers how data are distributed along the number line. So this is what we do when we look at the dispersion graph or histogram. One solution to the failure of maximum breaks to consider natural groupings of data. So they are more taken into consideration here, these natural groupings or clusters. The disadvantage are decisions on class limits are subjective. As there is no calculation, we look at the graph, and if different people look at the graph, maybe they would decide in different ways. So we would get different solutions at the end, different results. Depending on how the limits for each class shown in the legend are defined, there might be gaps. But this is the same disadvantage as usual, we can say. And before I start with the last one, this is the most complicated one. Let's take the break now. So then the last method, the optimal method of classification. So that sounds great right from the beginning, because it's the optimal method, then it should be the best method that we can find. But it also has some drawbacks, some disadvantages. But first, let's talk about the method and introduce it. Here, similar data values are placed in the same class and dissimilar data values in different classes by minimizing an objective measure of classification error. So the basic idea is the same as in the method we have just talked about, the natural breaks method. But remember, in the natural breaks method, it was subjective. So each person who's dealing with the data takes a look at this graph and decides subjectively, so based on their own interpretation. And these interpretations might be different. And to get rid of this problem, to solve that problem, in this method now, an objective measure of classification error is introduced. Therefore, we need more computation, but at the end, it's more objective. But the basic idea is the same. Dissimilar data values in different classes and similar data values in the same class. There are different measures of classification error, but one that is commonly used is the sum of absolute deviations about class medians. This is abbreviated as ADCM. Computing this measure involves calculating the median of each class. The median is the middle value in an ordered set. We talked about that, which is the sum of absolute deviations of class members about each class median, and then adding the resulting sums of absolute deviations. A smaller ADCM value indicates a better classification. So we have an example on the next slide. It makes it easier to understand, because if you read that text or if you hear that text, it's difficult to comprehend what's going on. But in fact, it's not difficult. You have done much more difficult mathematics in school, I'm sure. So this is the example, computing the sum of absolute deviations about class medians. So how we get ADCM. And we have in this example, we have this raw data. So it's just a smaller set, so it's easier to be computed. And we have here a comparison between quantiles classification and the optimal classification. And first, you compute here the error. That means you check out the lowest and the highest, and you compute the difference. So here, 13 minus 11 is 2, 32 minus 14 is 18, 100 minus 33 is 67. And then you sum that up and you get ADCM. And for the optimal classification we are talking about now here, you would classify in the first class of these data values, you would classify 11, 12, 13, and 14. So here the error is 4. That's even larger than in the quantized classification. But then in the second class, you have 31, 32, and 33, and you have an error of only 2 compared to 18. And the third class, you have 99 and 100. Here you have an error of 1, and here you have an error of 67. So if you have this raw data and you need 3 classes with optimal classification, you would get these absolute deviations about class medians of just 7. And here this is also described. In the just presented example, the optimal classification in 3 classes is obvious. For real-world data sets, it is necessary to apply computer-based algorithms for determining possible solutions. Afterwards, these possible solutions are compared and tested to find the best, the optimal solution. This is where the name comes from. The name of this classification method, optimal method. An algorithm that guarantees optimal solutions because of its mathematical foundation is the Fisher-Jenks algorithm. So this is named by the names of the researchers who developed this algorithm. It follows Fisher's idea that any optimal classification is the sum of optimal classifications of subsets of the data. So we look at subsets of the data, with not all data involved, just a part of the data is used, a subset. And so here are the steps then, finally, after this introduction. The first step, the algorithm starts with computing the sum of absolute deviations about the class median, ADCM. So we just talked about that in this example. For any ordered subset of the raw data, this is done now, for any ordered subset, ignoring how these subsets might fit into a particular classification. So we don't think about the final classification at the beginning. We take some of the data values, some ordered subsets, and compute this ADCM for them. Then in the second step, the optimal solution for 2-class map of the complete data set is computed. So we think just about the 2-class map. In our example here, we would need 5 classes, but we would start just with 2 classes, along with optimal 2-class solutions for subsets of the data. Then in the next step, these subset calculations are not used in determining the optimal 2-class map, but they are used to determine optimal classifications for maps with a greater number of classes, for example, a 3-class map. The number of steps depends on the number of envisaged classes. So if you want to have more classes at the end, then there are more steps. So this is just a description of what's going on. We are not computing this in detail. And then the final step, define the limits for each class shown in the legend. In general, there are again these 2 ways you know already. The question which number of classes is appropriate for a given data set can also be answered with the help of the optimal method. And this is very interesting and important. So for example, if the median is used as the measure of central tendency, the goodness of absolute deviation fit, GADF, can be computed. The goodness of absolute deviation fit. And you see how it is computed here. The goodness of absolute deviation fit, you have the ADCM, sum of absolute deviations about class medians for a particular number of classes. But you have also ADAM, the sum of absolute deviations about the median for the entire data set. The final number ranges from 0 to 1, with 0 representing the lowest accuracy. So a GADF value of 1 will result only when each observation is a separate class. So if you have, for example, in our case, you have an area, we have only 5 counties, and each county is in one class. We have a 5-class map. then we would get a GADF of 1. But this is equivalent to an unclassed map. So if you don't class, you have also 5 values. The GADF calculations can assist in selecting an appropriate number of classes. So this is what we want to know. How many classes are best for a certain data set? For example, construct a graph of the number of classes against GADF values in next slide, and look for a point at which a curve fit to the data begins to flatten out. At this point, a larger number of classes would not contribute substantially to a reduction in the classification error. So we will see that method. So you can use this kind of graph for the GADF. And you can, of course, if you have just one class, then it's 0. With 2 classes, it's about 0.4. With 3 classes, 0.6 approximately, and so on. And you see there is a point where the curve starts to flatten here, this angle. In the case of the foreign-born data, the curve appears to flatten out at about 5 classes. So this is based on the sample data for this whole chapter of classification with the foreign-born data of California. And here, the 5 classes, here the curve starts to flatten. The graph also helps determining the number of classes for which the GADF first exceeds a certain value, for example 0.8. This means the accuracy is 80%. In this example, a 6-class map could be appropriate, or for a GADF of 90%, a 9-class map. So if you want to have more than 80%, here is 80%, then we would have a 6-class map. Or if you want to reach 90%, then we would need a 9-class map. That's, I think, that one. So here is 90, should be that one. So it's very useful. We have exact numbers. We have a method that can be recomputed by any other person, and therefore all users should get the same result. All map producers should gain, not the users, but all the map producers, all users of the method, I mean, but not the final map users. So if we compute this, if I am doing it or you are doing it, we should get the same result. That's the idea, because it's based on strict rules. And this would be the final map then. So here along the number line, you see we have here these 3 classes. This is, I don't remember if it's exactly the same, but it's very similar at least to the natural breaks method. But then there is a difference here in how the rest of the classes is computed. This is also again the same, so the outlier is in one class, one number in one class. But here I think the exact breaks are a bit different. And yeah, it looks similar to natural breaks, but now it's based on hard facts, let's say, and not on soft interpretation of the map producer. The advantages. Now, this method considers in detail how data are distributed along the number line. It is the best choice for classification when the only intention is to place similar values in the same class and these similar values in different classes. It can assist in determining the appropriate number of classes, which is important, and it can assist in comparing and assessing different classification methods. This is also an interesting aspect here. Disadvantages. So there are still disadvantages, although it is the optimal method. It's a bit difficult to understand the concept. So also for you, but this is in part due to the use of a foreign language, but it's a bit difficult to understand what's going on here in this method. Computation needs more time and resources. So usually you need computer, which is not a big deal nowadays, but still it's more complicated. For efficient use, a software package is necessary that includes the optimal method of classification as an option. Then it's relatively easy if you have this available. Depending on how the limits for each class shown in the legend are defined, there might be gaps. But yeah, I talked about that. You have this problem with nearly all of the classification methods. Now, I've just mentioned the GADF technique can also be used for computing the accuracy of other classification methods. And this is, of course, very interesting now for us because we can better compare the different classification methods. The first example, the result of the optimal method of classification can be compared with the result of the quantized method of classification. If the computed GADF values are similar, it might be better to choose the quantized method because it would be easier for the user to understand how the class limits were created. Second example could be to improve the quantized method, GADF values can be computed for various numbers of classes to assist in determining an appropriate number of classes for that method. So this is also possible. So you can use it for the different methods to improve them, not just comparing different methods. Now, criteria for selecting a classification method. Any rating system for classification methods is influenced by the computer setting the map maker has available and the knowledge of the map user. So this is important to keep in mind. Assumptions for this rating that I will present you here from Slocum and colleagues. First, computer software is available for creating all of the classification methods. Second, map user is a college-level student with a basic foundation in introductory statistics. So what is a mean, what is a standard deviation is clear, for example. And third, all classification methods are applied properly, of course. So for example, mean standard deviation in the table only with a normally distributed data set. Conflict of objectives between ease of understanding legend, this is best with no gaps between class limits, and legend values match range of data in a class, usually best with gaps between class limits in legend. So here is a conflict, and it depends on how we decide. Legends for equal intervals and mean standard deviation method are without gaps, and therefore legend values cannot match the range of data in each class well, but they are easier to understand from that point of view. Or B, legend for quantiles, maximum breaks, natural break, and the optimal method usually contain gaps. because their legend values, sorry, because their legend values are chosen to match the range of data in each class. But it is also possible to close these gaps by computing new intermediate class boundaries between the old ones. At the same time, the advantage of legend values matching the range of data in each class is largely lost. Accordingly, the rating in the table would change. But this depends on how you see the situation, what you prefer for your users. If you produce a map, a visualization, and you need such a classification, you always have to think about the users. Are they familiar with the methods or not? Is it a problem for them to have gaps in the legend or not? And this then is the final rating here of the different methods for different criteria. And of course, we can use this criteria then for selecting a method of classification. I have only slightly modified this assessment, let's say, of the methods from Slocum and colleagues. So we have the six classification methods here: equal interval, quantiles, mean standard deviation, maximum breaks, natural breaks, and optimal. And we have here the criteria. So considers data distribution along number line, ease of understanding the concept behind the method, ease of computation of the method, ease of understanding the legend, legend values match range of data in a class, acceptable for ordinal data, assists in selecting number of classes. So these are the criteria. They are all from Slocum and colleagues. And you have this color scheme here, also with letters. So P is for poor, G for good, VG for very good. This is, so these three, and there are two here with no or yes, because, for the especially acceptable for ordinal data, it's acceptable or not. So there is no further grading here. And what I've just talked about in the slide before, ease of understanding legend, and legend values match range of data in a class. So you can only have one of them. So if here it's very good, then here it's poor. If it is poor here, then it's very good here, usually. There is one exception here. Here it's just good understanding of legend, because with these standard deviations in the mean standard deviation method, it's sometimes a bit strange for users what that means. So if you're perfectly familiar with standard deviation, then it would be very good here. So this is the problem, of course, with this assessment, that it depends in part on the users. And so we have a general assessment which should be varied a bit depending on the kind of users and the kind of situation where this method is applied. And I don't want to go through each of the positions within this table now, but a few comments. So, of course, if you use the computer and all algorithms are available, the ease of computation is very good all the time, but there is no differentiation here. We have these 6 methods, one after another. I've introduced them to you. And the first 2, equal interval and quantile, they are poor when it's about the distribution along the number line, so if it's considered or not. These 2 methods, they are blind for the number line. They do not know what's going on along the number line. It's better with mean standard deviation and maximum breaks, and it's best with natural breaks and optimal. And this is, of course, one of the most important criteria. The concept Generally speaking, it's more complicated towards the end, the later methods, the natural breaks and optimal, but also the standard deviation is sometimes a bit more difficult. But it's not, it depends on the knowledge of the users, of course, if it's easy or not to understand the concept. If you're already familiar with them, you can say it's all of them is very good, no problem. But if you're not so familiar with them, then of course these three methods, equal interval, quantiles, and maximum breaks, it's easiest to understand. And the legend, it's easiest is equal interval, of course. You have always the same interval, so there's nothing complicated there. With standard deviation, if you are familiar with the concept again, then it's usually not difficult to understand the legend. Then you could also give a very good here. It's a bit more complicated with the other methods. And we talked about that, so you can change that if you like. So if the legend values match range of data in class, it's not possible with an equal interval, but with the others you can also change the numbers in the legend a bit to have a better fitting here. Which is what is very interesting, I mentioned that before, is the acceptance for ordinal data. So the only method acceptable for ordinal data is quantiles. So this is the only yes here. This is important to know. If you have ranked data, ordinal data, then if you need a classification, use quantiles. Yeah, and this assistance in the number classes, we talked about that. So best is the optimal, second best is natural breaks. With the others, there is no assisting. So this overview is it's important also because think about the method. It's important that you understand what's going on. What is the basic idea of this method? If you know that, then you should also be able to classify these criterions along these different criterions to classify these methods. And finally, just to compare the maps, a few words about that. So you have seen quite different classifications here. We have always the same data. We have always 5 classes, but the maps, they look totally different. So these are the first 2 methods, equal intervals and quantiles, then mean standard deviation and maximum breaks. And at the end, we have the natural breaks and the optimal method. And you see these 2 maps, they are quite similar. There are only few differences within this sample data. For example, this county here is classified in different ways, but it's nearly the same at the end. And of course, you might ask then why it is necessary to do all this computation. With the natural breaks, you do it just visually with the histogram, with the number line. Here you need some computation, and it's much more complicated to understand the concept behind it. And the result is nearly the same. But this is, of course, true for this data here. If you use a more complicated set of data, just imagine you have the counties of the whole of the United States. Then it becomes much more difficult. And here also a comparison of number lines. So the first 3 equal intervals, quantiles, and mean standard deviation. You see here there are no gaps in our examples. All classes, if one class ends, the next class begins at the same position. Here you see, of course, equal interval. That's easy to understand. Then quantiles, about the same number of counties which in each of the classes. Then the mean standard deviation. Here it doesn't work, so it would be a big mistake to apply this method for this kind of data. So remember, you need a normal curve. You need the bell-shaped curve here, a normal distribution, and we have a positively skewed distribution here. And therefore, don't use mean standard deviation if you have such a distribution of data. You have only 3 classes here on the number line. Class 1 and 2, you remember it was about negative numbers, or there are no negative numbers here. So you immediately see there is something wrong. And the last 3, you have the maximum breaks, natural breaks, and the optimal median is an optimal method based on median. There are other ways to do it. I've just introduced this easiest version and the most common. And you see there are nearly no differences here in the classification. So it's very similar. And there is only a smaller difference between maximum breaks and natural breaks. And one thing that they have in common here, now here you have the gaps. You have some large gaps like here between class 4 and 5, and smaller gaps here between the lower classes. So this is a characteristicum for these 3 methods. Again, you can compute here a number in between. You can say, okay, let's use 30 because it's a nice looking number in the legend. But in fact, you're reducing the information for the users then. So this is the end of the chapter about classification. Do you have any questions about these methods? I'm sure you have used some of those methods before, others maybe not. And they are important for several other visualization methods. Of course, they're typically used for the choropleth map, but you need to classify numbers for many visualizations. Therefore, this is a kind of basic knowledge if you want to work with data visualization. Well, how to choose the best one? The last method, the optimal method, will give you some assistance. So you can use this curve, for example. So this curve is very important because it can help you to find the optimal number of classes. So in our examples here, we had always 5 classes. But if you have a new data set, you have to decide how many classes should I use. And with this graph, you can easily find the optimal number. And therefore, the optimal method is a great choice, but it's more complicated. It's harder to understand for the users. And for the visualization at the end, of course, other factors play a role. So I'm talking just about the classification here. There should not be too many classes. So remember, we talked about this problem also in the chapter about perception. So if you have just gray values, for example, you should not have too many classes, because then it's hard to find these gray values in the map. So in this chapter here, there is no information about that. So it's for sure not good to have, for example, here these 9 classes to reach 90%, but in the map you have then too many gray values, for example. So and it's hard for the users to compare or to find the exact numbers then. So if you have this gray value in one of the administrative areas, for example, in the counties, and you don't know which gray value is it class 3 or class 4? Because these gray values are too similar. Therefore, you should not have too many classes. So from the visualization point of view, there are other aspects, other criteria you should take into consideration as well, not just which classification method or how many classes. Also, which colors you use for a legend, which kind of color scheme. So these are more than questions about the visualization. And these criteria here is this assessment of the different methods. This should help you, in fact, to find the best method in your situation. So this curve that I've just shown to you, where you can find out how many classes you should use, this you can use for all the methods. So you can, for example, you can decide for quantiles, because you have ordinal data, that's easy. If you have not ordinal data, if you have, like in this situation here, you have, for example, the foreign born, and you decide to use, for example, the natural breaks method, you can still compute with this curve the number of classes that you should use. Here it is fixed, again, here it's fixed 5, but this is just to compare the different methods. If you have data, for example, for China, for some administrative areas, some districts, or I don't know how they are named in China, you have the provinces, and then you have levels below provinces. And I just call them districts. So how many classes you should use for a map of China or a map of Hubei? You can use, you can decide for natural breaks, for example, because it's important for you to consider the data distribution along the number line. This is then a better result. And it's important for you that it's fast. You don't need much computation here. And the legend values match range of data in class. This is, of course, it has to do with this first one also. And but still, it can help to compute this curve, this GADF curve, to get the information how many classes you should use then within natural breaks. So some of the methods are easier to understand, others are a bit more complicated. Yeah, you will find many maps that use equal interval or that use a method that is even not clearly defined. So it's sometimes a kind of mixture. You have some, you use natural breaks, but it's somehow mixed with maximum breaks. So people do not really compute all of this. They just look at the numbers and decide, okay, I classify in this or that way. So natural breaks has a disadvantage that it's a bit subjective. So it's the interpretation of the map maker that plays a role. It's not just the computation, or there's not really computation at all. So yeah, I hope I could answer your question. So when it comes to visualization, again, there are more criteria, not just the criteria here. These criteria here are about the classification method only. So there are no aspects of visualization. When you compare the different maps, then you see they look very different. And of course, usually we don't want to have such a map. It's a bit boring. So many of the counties are in the same class. There's no differentiation. If there is no differentiation in the map, it's difficult to analyze this data. What can you analyze here about the spatial distribution? You just can say, okay, it seems it's higher towards the south end of Florida, but you cannot interpret any distribution differences within this huge area here because they're all in the same class. Here, this is much better. So here you can better interpret a pattern here. But you see another disadvantage. You know this county here, it has an outlier value, a very large value compared to all the others. And this is covered here. So it looks they have more or less the same value, but we know they don't have the same value, even not near to each other, because the range here is too big, 6.8 to 45. That's too huge. So you put things in the same class that are too different. They are not similar at all. So therefore, it's important, this criterion considers data distribution along number line. This is important. And these two methods, they're not doing this. And you see that here. Now, mean standard deviation, we cannot really compare here because it's the wrong method for this kind of data. With maximum breaks, we have in part the same problem here as we have with the equal interval as this one. So in fact, the map of A and D are a bit similar as there are so many counties with the same value. They're in the same class, so it seems they have the same value. The value range you see here, you cannot see these differences. But it's based on the maximum breaks. So according to the interpretation or in the taking into consideration the number line, the distribution of all the data, this is a good solution. But if you want to have more details here, then it's better to use another method. And for me, these two are the best here because they show you the outlier. You have still a better differentiation in the smaller numbers. So you see pattern here as well. So here along the coast, for example, there are higher numbers. This is something that's interesting if you want to analyze the data, if you want to analyze the data. And it's not there. So this information is lost. And for me, these two are best. But if you have users that cannot understand the concept, what are natural breaks? What kind of legend is this here? Usually we don't get the information what kind of method has been used. So usually we have a map and we have a legend. And just from the numbers, I could not say this is natural breaks. As you see here, the numbers are very similar, for example, to optimal. So just from the numbers, I cannot say that. But I can notice here, okay, it seems the distribution has been taken into consideration for this classification method. And that's important. And the gaps here, it's mainly something people should get used to, because it's better to have the gaps between the classes. But in many newspaper maps or tables, they prefer to have some nice numbers here, for example, from 0.5 to 3, then from 3 to 5, and then from 5 to 9, and then from 9 to 16, and then from 16 to 50, something like that. It looks nice, but you get less information then, in fact. But for some users, this might be more important, because they are too irritated by that. If we talk about scientists, researchers, students who are interested to analyze the data, to get the most out of it, then it's better to work with this kind of numbers. So accept the gaps, because then the numbers in the legend are more precise. And for this data set here, finally, I would use natural breaks, because it's easy. You don't need the computation. The result is good enough to interpret this area, the data for this area. And yeah, but with other data, with more complicated data, it might be more important to have an approach like the optimal method, where you can exactly compute everything, and it's not based on individual interpretation like it is here. So I hope this answers your question. And yes, it's even break time. Sorry, I was too much in the answering of your question, so I didn't notice the time. So then let's have the break a bit longer, or not longer, I mean the same length, but we will start again a few minutes later. Then it's let me compute that. Our next topic is choropleth mapping. And of course, classification is very important for choropleth mapping. Usually you classify your data, and therefore you need the methods we have just discussed in the last chapter. So again, I use the book of Slocum and colleagues. What is choropleth mapping? This method is commonly used to portray data collected for enumeration units, such as countries or provinces or counties or districts, anything like that. So they're also named administrative units instead of enumeration units. Enumeration unit is a bit more general. So if you, for example, use a grid system with hexagonal grids or square grids, for example, that's also possible. So then you have a number for each square, and all the squares cover a certain region. For example, for taking probes within a lake, you divide the lake in squares, in small square-shaped areas, and then you take samples and to get the information, to get the data of, for example, certain kind of fish or whatever, then you can also call these enumeration units, but these are not administrative units. Therefore, this term is more general. It is most appropriate for a phenomenon that is uniformly distributed within each enumeration unit and changes only at enumeration unit boundaries. So that's also important. So here it's most appropriate. So sometimes it's used for other phenomena as well, but this would be the ideal situation. If a phenomenon is not uniformly distributed within each enumeration unit, it is only possible to focus on typical or average values. The still raised impression of uniform distribution by this mapping technique is then misleading. And of course, the greater the differences are within one of the units, the more misleading is it to just represent this unit with just one, for example, gray value. Because then you have the impression you have the same data values everywhere within this area, but it might not be true. If size and shape of enumeration units vary significantly, also the potential impact of inhomogeneous distribution varies. It is larger in larger units which additionally have the biggest visual impact. So you have to take this into consideration as well. Differently sized enumeration units also cause misjudgments of value differences between them if raw data values are depicted. Therefore, it is important to adjust or standardize raw data to account for varying sizes of enumeration units. We have this problem, for example, right now. There are many maps around in the internet about the spread of the virus. And you get numbers for different kinds of enumeration units. So sometimes you have numbers, for example, for the different provinces in China. Then you have numbers for different states within the United States. Then you have numbers for the countries in Europe. Of course, there are maps in each of the countries, or for each of the countries in Europe, you can find maps that show you the distribution of the data within these countries. So based on the next administrative level, like in China for the provinces or in the United States for the states. But of course, the size of these units, they vary greatly. So if you have a world map and you have there are small countries, some very small countries like in Europe, and compare absolute numbers of infected persons with other areas that are large, whole countries. For example, you have whole of Russia, and then you have for China, you have the provinces, and so on. So the size of these units is very, very different. And to compare absolute numbers here is totally misleading. These maps are really bad, and you see them everywhere now. So this is just why we have to standardize data, to make data better comparable, because the units are different, and therefore here it's not so much about the size, because we talk about people. So it's about the population numbers. So there are some small areas like Singapore where the population is relatively high, so the number of population. But there are other areas quite big with low population, like Russia. But it's different if you compare Russia with China, because in China there live so many more people, and so on. So this is exactly the problem that we face. And there are different methods of standardization to solve that problem. So we have to talk about standardization first. Methods of raw data standardization. So it's possible to divide area-based raw totals by the areas of corresponding enumeration units and compute percentage of enumeration area, therefore. Example would be instead of forested land in square kilometers, you can use percentage of forested land of each enumeration unit. So this makes it comparable. Then you don't compare different absolute numbers, which of course are different for areas that vary greatly in size. This is not about population, this example, this is about area. Or dividing area-based raw totals by other corresponding area-based raw totals. And, for example, compute percentage of a more general area-related category. An example would be, instead of area covered by a bamboo forest in square kilometers, percentage of bamboo forest of total forested land in each enumeration unit. So this is also possible. Or dividing other not area-based raw totals by A, the areas of corresponding enumeration units, or B, some area-based raw total, computing a density measure. Examples for A, instead of apple growing area in square kilometers, you can use harvested apples in tons and divide these numbers by the enumeration unit area in square kilometers to get harvested apples in tons per square kilometer for each enumeration unit. And then you can compare these numbers. So you make numbers comparable so that such comparisons make sense. That's the idea of standardization. Or B, instead of apple growing area in square kilometers, use harvested apples in tons and divide these numbers by the apple growing area in each enumeration unit in square kilometers to get harvested apples in tons per square kilometers apple growing area for each enumeration unit. So you see there are many ways to do it. Of course, the result is not the same, and you have to take into consideration, you have to think about what really is it that you want to compare. Or, different situation again, dividing other not area-based raw totals by other corresponding not area-based raw totals. And, for example, compute percentage of a more general not area-related category. Although area is not included in this method, this approach indirectly standardizes for area because larger areas tend to have larger values for both attributes. Example here is instead of people growing area, instead of, this S is wrong, instead of apple growing area in square kilometers, use the value of harvested apples in US dollar. Then divide this number by the value of all harvested fruits in each corresponding enumeration unit in US dollar and multiply the result by 100 to get the percentage of the value of harvested apples on the value of all harvested fruits for each enumeration unit. So this is also a situation that's common. And with the numbers of infected people with the SARS-2 new coronavirus, you can, of course, also standardize by using percentage of the population. So how many percent of the population are infected by the virus? Usually these numbers are very, very small, and therefore instead of a percentage, the number given is often you have a number of cases compared to 100,000. So how many of 100,000 people are infected? This is a typical number, and this makes it comparable. The absolute numbers are also interesting because we see a bit how fast the virus spreads. For example, there are countries with some people infected. But to really compare the numbers, you need to standardize them. That's very important. Be aware that different standardization methods may lead to quite different maps of the phenomenon being investigated. So there are examples on the next slides. It is our responsibility as map makers to think carefully about which standardization method is most appropriate given the data and the message that we wish to communicate. And of course, also the audience. So who are the users? What about their background knowledge, their skills, and so on? As the different standardization methods produce different views of the data, it might be interesting to use them to gain better insights into the data. For example, with exploratory data analysis environments. So sometimes it makes sense to produce several maps and compare them, because each of the map will give you a different view of the data. So this can be very interesting for analysis. Examples for different standardization methods. So we have here another US state. This is Kansas, and it's about the wheat harvested there in 1993. And A, so this is example A, dividing acres of wheat harvested by acres of wheat planted. Both are area-based raw totals, and thus the results are proportions or percentages. The ratio of harvested to planted acres reveals a more random pattern. Lower values extend across the northeastern and north central sections of Kansas. So here in the northeastern and north central, here north central, here northeastern section, here are the lower values. Here you see the legend. You get a ratio of harvested to planted acres. So it's a percentage. You can reach nearly 100, but sometimes you can imagine there is more wheat planted, but due to, for example, climate reasons, so it was too dry that year, or there was some problem with some animals destroying part of the planted areas, then the harvest is lower. So here the lowest numbers are just a bit over 50%. The rest is lost. So this is interesting, of course, for taxes, for support of the state for the peasants, and so on, and also to compute how much harvested wheat is there on the market, how much wheat is there on the market at the end, and other questions. Then the next example, now dividing bushels of wheat harvested by acres of wheat harvested. The result is a density measure. So you get bushels per acre. So what are bushels? Here you have information about that. 20 bushels per acre correspond to 1.35 tons per hectare. And 50 bushels per acre correspond to 3.36 tons per hectare. So it's another kind of unit, simply. The map of wheat yield produces another pattern with progressively higher values as one moves westward across Kansas. So now we have this bushels per acre unit. And of course, we have now different numbers, and also the map looks different. So here are the low numbers in the east and the higher numbers in the west, southwest area. Now, after talking about standardization, an important decision with respect to choropleth maps is whether to produce a classed or unclassed map. A potential advantage of an unclassed map is that it can more accurately portray the data. For example, on a gray tone map, the intensity of a shade can be related directly to the magnitude of individual data values. The potential advantage of a classed map is that the limited number of categories makes the map easy to process. It is also important to consider whether the final map will be presented to others or it will only be explored by yourself. So we talked about that. You can use maps and visualizations in a very early stage, just to get a first impression of the data, for example, a quick and dirty version that is not produced for any other uses. It's just produced for yourself to get some insight into the data. Or later on, you have a more elaborated version with some results of your analysis, for example. And then at the end, you have a final version that's perfectly made for a certain user group to communicate your results to them. And of course, the maps will look different. And also you can use different classification methods for them. After choosing an appropriate classification method and number of classes, depending on the kind of data, the intended purpose of the map, including the audience to be addressed, also an appropriate color scheme has to be selected. An important source for information about color schemes is the work of Cynthia Brewer and her colleagues. Together with Mark Harrower, she also developed the tool Color Brewer in 2003 to assist in selecting appropriate color schemes. For the latest version, you can check out this site in the internet, colorbrewer2.org. This is a screenshot, but not of the second version, but of the first version from 2003. And here you have enumeration units. As you see, it's a part of the United States. And this is just to check out different color schemes. So you can define the number of classes you want to have. Then in step 2, the legend type, sequential, diverging, qualitative, and there's some additional information, learn more. So this assists you in choosing the right legend type. And then you can apply these different options here of color sequences. These are sequential. Schemes, and you can get the numbers here in different systems. This is cyan, magenta, yellow, and black. This is red, green, and blue. This is a hexadecimal system, and so on. There are different systematics for colors, and then you get the numbers here. So this here is obviously in the this. Yeah, it's also given here. Is the subtractive color scheme, and you get the specified numbers here. So this is for cyan, this is for magenta, this is for yellow, and this is for black. So it's just 20% here, 20% yellow, and no other colors are involved for the first color. So you get all this information, and you can check out the schemes, and you can use then these numbers, for example, in your own mapping system, if you like. And you can also change the map a bit, and you see how it works with overlays of streets, certain colors, combining here red and blue. You know, red and blue is not good on screens. We talked about that. It's a very, very good application. The kind of data influences color scheme selection, of course. So if you have unipolar data, then you should use a sequential scheme, a variation of color value or lightness, alone or in combination with a variation of color saturation. Use light or bright colors for low data values and dark colors for high data values. Or you have bipolar data. Then it's better to use a diverging scheme. These schemes consist of a variation of color value, lightness of two color hues that diverge from a common light hue or neutral gray in the center. So you have a diverging point in the center, like combining two sequential schemes running from the center to the two ends, with the lightest tones toward the middle. Or if you have balanced data, you can merge two sequential schemes or using a diverging scheme to emphasize the midpoint of the balanced data. So that depends. Here you have a comparison now of two sequential color schemes. The topic is here about adults not graduating from high school in 1990. So it has to do with the education level in the United States. It's based on the data of the states. And you have a percentage, and only lightness, the color value, varies here. Although lightness or color value differences should predominate for sequential schemes, it is possible to enhance visual contrast by adding saturation differences. So you can see that on the next slide. Now, it's not a big difference. I switch back and forth again. Just check out here the legend, compare it. So it is only a slight difference here. So they mix it now a bit with saturation. So it's lightness and saturation. Both vary now. The saturation increasing from the first to the third class and then decreasing from the latter two classes. It is important that higher saturated colors do not overemphasize less important categories. Now, this is an example for a diverging color scheme in which two sequential schemes converge on a neutral gray. You have a central class, a center class. It's a gray value, and you have, in fact, two sequential schemes, although they're quite short, just two classes on each side. So we can say this is sequential, but altogether it's a diverging color scheme because it diverges in two directions from a diverging point in the center. So although such a scheme works best for bipolar data, it is applied here for unipolar data because we have still the same topic, adults not graduating from high school. Such a solution is possible when a classification method is used that places the median and or the mean in the middle class. So a logical dividing point is created, and the unipolar data can be treated like bipolar data. So you have this mean or median here in this class, in the center, best is in the center of this class, and then you can compute all the other numbers as a bipolar scheme. And now we have a U value series here. It's still the same topic, adults not graduating from high school. To examine the role that color schemes play in map use tasks, Janet Mersey had map readers interpret a spatial distribution using a variety of color schemes. She found that for unipolar data, the sequential U value scheme shown here worked best in the majority of tasks. So this is an empirically proved best solution for this situation for a majority of tasks. That means not for all tasks. You can ask different questions, of course, about such a map. You can do analysis in different ways, and therefore different maps might be the best solution. But for most of the tasks, this scheme works best. And this map is not from the original study, which used another unipolar data set. The map shown here was produced for the book that I use here they used different data to make it better comparable with other choropleth maps shown. So they used here the same data and the same area, the United States, to make this map better comparable to the others. But it is this kind of scheme. It's a U value series. So you have light and dark, but you have also from yellow to red. So this is from yellow to red means U series, and from light to dark means a value series. And these two aspects are combined here. And this gives you the strongest impression. Because of the high cost traditionally associated with producing colored printed maps, considerable research was undertaken in the past on selecting appropriate aerial symbols for black and white choropleth maps. Of course, today we have this problem not so much, especially if you produce maps for displays, for computers. We can, of course, use all the colors, no problem. But back then, it was much cheaper to produce black and white maps, and therefore, there was a lot of research about that. This research resulted in gray curves or gray scales, which express the relationship between percent area inked and perceived blackness, which is not linear. At the light end, a small difference in percent area inked equates to a large difference in perceived blackness. At the dark end, it's the opposite. So here, a large difference in percent area inked equates to a small difference in perceived blackness. So if you check out such a gray curve, or here you have two of them, the gray curves of Mansell and Stevens, for converting desired perceived blackness to percent area inked. So percent area inked means, for example, you have 80% black in a certain area, or 90%, and so on. So these curves are intended for fine-toned black and white aerial symbols. And you see here, this is the percent area inked, and this is about the perception. So this is the perceived blackness. If it would be linear, then you ink 50% and you have the impression of 50%. But it's not linear, it's different. So you have to ink here in the Munsell, on the Munsell curve, you have to ink about 65%. No, sorry. If you ink 50%, you have the impression of 65%. And if you want to have the impression of 50%, you have to ink about 35%. And these two curves are also different, of course. So under different situations, they got different results. And important is here the light area, so the perceived blackness, if it's very low, you have to ink more. So you have to ink, no, sorry, it's the other way. You have to ink less. So if you ink 5%, you have the impression already of 20. So here this difference is quite huge, this difference between the percentage inked and the perceived. And here on the other end, it's the opposite. So here small differences in the area inked result in nearly no difference in the perceived blackness. So you have to choose greater differences if it's very dark. So if you have, for example, here 80% inked, you have, depending on the curve, you have about 90% here. But if you choose 90, it's just a little bit more. So the difference here is lower. Therefore, you need greater steps here to get the same impression here. And yes, you should keep in mind that if you specify a particular percent area inked using software, there is no guarantee that hardware will actually produce the same percent area inked. So if you use some software for mapping, and you can exactly give the number you want, you say, okay, I want to ink 90%. It does not mean that on the screen you actually see exactly this 90%. So the hardware might produce a value that's a bit different from that one. Analyze available hardware carefully to ensure that percent area inked specifications match software specifications, and that black marks are actually black marks in the final product. So of course there are more expensive devices where you have where these numbers correspond better. So keep that in mind. Not everything that can exactly be defined really at the end gives you such an exact result. The decision whether a choropleth map should better be classed or unclassed depends on the answers to the following two general questions about the goal of the map. First, should the numerical relations among all data values be maintained? Yes, then it's better to have an unclassed map. No, then it's possible to produce a classed map. Because some of these relations are always lost if you use a classed map. Is the map intended for presentation or exploration? If it is for presentation, then usually a classed map is better. While for exploration, you can also use an unclassed map. Because, for example, also with interactivity, with mouse over effect, you can get exact numbers, of course, in the area. And 2 questions about the map and data characteristics. How many enumeration units are in the choropleth map? A large number of enumeration units will more likely cause difficulties to read an unclassed map because it influences the number of gray values needed. Simultaneous contrast problem. And the 4th question, how are the data values distributed along the number line? The dispersion graph, we had that in the chapter about the classification methods. In an unclassed map, a more skewed distribution might hide ordinal relationships in parts of the data because of a higher number of similar gray values. Here now you have a comparison of a classed and an unclassed choropleth map. The topic is here foreign-owned agricultural land for 1992 in the United States based on data of the states. And the optimal method was used here for the classification to create the classed map because the optimal method does the best job of minimizing classification error, and so, in theory, will produce classed maps that are most similar to the unclassed maps. Shades for the classed maps were selected using a conventional maximum contrast approach in which tones are perceptually equally spaced from one another. So these tones here, these gray values, they should be about equally spaced from each other. And this is the percentage of privately owned land in the different states. And now we have an unclassed map for the same data. Percentage of privately owned land. Shades on the unclassed map were made directly proportional to the values falling in each enumeration unit, thus maintaining the numerical relations among the data. The difference in the 2 maps is a function of the severe skew in the data. The unclassed map is a spatial expression of this skew, as we see numerous low-value gray tones and just one black tone. So you see here, these areas are very similar. This area stands out as an outlier. And if you compare, I go back a step. So of course, the differences are more emphasized here, which might be useful for analysis, but in some situations might be misleading. So you see here the comparison of classed and unclassed choropleth map. This is the number line. And you have the percent of privately owned agricultural land that is foreign owned here. And you have the states now of the United States. So each dot here is a state of the United States. And you see it's positively skewed. So it's very similar to our example from the classification chapter. The difference in the 2 maps is a function of the severe skew in the data. The unclassed map is a spatial expression of this skew, as we see numerous low-value gray tones and just one black tone. So just this here is the black tone, and here you have many similar gray values. So perfect. We have finished this chapter, and also the time runs out now. And yeah, I want to thank you again for your interest and hopefully your concentration abilities to follow my speech. Again, if you have any question, please, you can contact me anytime. Just write me on QQ or QQ Mail, whatever you prefer. And I hope you all stay well, take care. Now in this opening up area within Wuhan and Hubei. And yeah, all the best, and I wish you a nice rest of the week. And yeah, I hope to see you. I cannot say, but hope that all of you will be back in this course next week. So thank you, and goodbye.